Let's do problem number 59. Suppose a solid disk of radius r is given an angular speed omega initial about an axis through its center and then lowered to a horizontal surface and released as shown in the figure. Furthermore, assume that the coefficient of friction between the disk and the sphere is mu. A. Show that the time interval before pure rolling motion occurs is r omega initial divided by 3 mu g. And B. Show that the distance the disk travels before pure rolling motion is r squared omega initial squared divided by 18 mu g. And that's what the diagram looks like. Let's start by drawing our diagram. You have your solid disk that is rolling on a horizontal surface. Right in the middle of its center of mass, you have its weight going straight down, and from the surface to the top is your normal force. It is rotating that way, and then you have friction acting on it over there, and we can call that mu times the normal force. And since it is not rotated on its axis or anything of that sort, the normal force is just going to be mg, and so the force due to friction, you can just write it as mu mg. So how do you solve this problem? Since it is a disk rolling across a horizontal surface, we know there's gonna be torque coming into play because of friction. We know this is gonna have something to do with angular momentum. And since we need time, this is gonna have something to do with momentum for sure, because they want to solve for time. And so with knowing that you are thinking about torque and angular momentum, you need to think about an equation that has both of these, and that would be force equals the change momentum over time. And so using this equation, you're going to need to isolate time. So let's do that. Isolate time, and you get change in momentum over force. And so what is change in momentum? Change in momentum is simply going to be final minus initial. Your initial momentum is going to be 0, because at the very beginning, when this thing is dropped onto the surface as described in the problem, it is not translating. It's only after a while that it starts gaining ground and translating in the x direction. But since it is not translating initially, it has no initial momentum. So the only momentum is the final momentum, and that will be mv. And you know that v equals r omega. So let's rewrite it in its rotational equivalence, which is mass, angular speed times radius. So you can plug that into your change of momentum, and the only force here, the only real force that we are concerned with is that force of friction. So it's got to be that in the bottom. So let's write that. Change in time equals m omega r over mu mg. The masses will cancel out, and so you'll be left with the change in time equals radius omega over mu g. And this omega here is actually going to be omega final, but you're only concerned with the final angular speed, since we ruled out the initial momentum doesn't matter, and that only the final momentum matters. That means we only care about final angular speed. So now we need to solve for final angular speed, and once you do that and you plug your stuff in, once you find out what's omega final and you plug in, you'll be able to get that. So if you look at this, you can see that we're on the right track. In the problem, they want us to get r omega initial divided by 3 mu g. And as you can see, we have every single one of those variables except omega final is the one thing that we're not supposed to know. So we need to come up with an expression for that can replace omega final that has omega initial. So if we think for a little bit, we can think about just, how I said torque is going to have something to do with this problem. A little bit arbitrary, but just start by summing your torques, and that will get you somewhere. So if you sum your torques, you get the torque due to friction equals I alpha. The torque due to friction, torque is just Rf sine theta. And since friction is applied at a 90-degree angle, don't have to worry about that. Your torque due to friction is just going to be R mu mg equals moment of inertia of a disk is half mr squared. And so we're not going to write alpha, because if we just write alpha, that's going to be useless. We need another way of working with alpha. So again, a little bit arbitrary, but since this has something to do with time, we can start thinking about kinematics. So if you thought about this kinematic equation, then this can get you somewhere. So isolate alpha and you get omega final minus omega initial divided by time. And you can plug that in here, and this will get you somewhere. And now that you're here, you can start combining like terms. So immediately, 1r can cancel, and the masses will cancel. And so what I'm going to do is multiply both sides by 2 and t to make this look a little bit nicer. So I forgot to add the negative there. It'll be negative 2 mu gt. And once you multiply it over the 2 and the t, you can distribute the r. So you get that equals to r omega final minus r omega initial. But this still doesn't get you anywhere, because omega final and you have this, mu gt, this doesn't get you anywhere. So you need to come up with another way to write all of these variables. So again, also a little bit arbitrary. Sum your forces in the x direction. You'll get the force due to friction equals ma, or negative mu mg equals ma. Cancel out the masses. You can rewrite acceleration as final velocity over time, and you can set that equal to negative mu g. Final velocity, because we only care about final, because we already ruled out that initial doesn't matter. And once you're here, you can multiply both sides by t, and you'll get final velocity equals negative mu gt. And you know that velocity is equal to r omega. So r omega final, again, only final because that's all we care about, equals negative mu gt. And well, look at that. You have negative 2 mu gt and negative mu gt. Well, that's telling you that this is negative 2 r omega final. Isn't that nice? And then you can combine these omega finals. So your negative 2 omega final, well, that just gives you negative 3 omega final equals r omega initial. You cancel the r's, and you'll get omega final is equal to 1/3 of the initial angular speed. Okay, you finally have omega final in terms of omega initial like the problem wants, and you can plug this right into there and answer the question. So the answer to part A is delta t equals r times omega final, or we'll just put that in, omega initial divided by 3, all divided by mu over g. Well, put that 3 down there, and your final answer is delta t equals r omega final over 3 mu g. And this matches exactly what's in the textbook. Part B, show that the distance the disk travels before pure rolling motion occurs is r squared omega initial squared divided by 18 mu g. So to solve this, you need to use energies. You need to realize that from the moment this thing hits the ground, it's going to start rolling. And it's going to stop rolling at a certain point because it lost its kinetic energy to friction. Friction took away the kinetic energy. So if all the kinetic energy eventually went away because of friction, you can write that the change in kinetic energy is equal to the work done by friction. The friction took away all that kinetic energy. So once you write this down, it basically solves itself. Half mv final squared equals the force due to friction, which is mu mg, times delta x, since work equals force delta x. And now you're just solving for delta x. One mass cancels out, and you can rewrite velocity final as r omega, since velocity equals r omega. So you can write half r squared omega final squared equals mu g delta x. Multiply the 2 over, r squared omega final squared equals 2 mu g delta x. Move the delta x to the other side, divide everything by r squared omega squared. Just keep things rolling, you get delta x equals, other way around, divide that over there. Delta x equals r squared omega final squared divided by 2 mu g. And then for omega final, you will plug that in and square it, which will give you equals r squared omega initial squared divided by 9 over 2 mu g. And then you can move that 9 down there. You'll finally get delta x equals r squared omega initial squared over 18 mu g. And this matches exactly what's said in the textbook. And this is how you do problem number 59.